first one, if the population is normally distributed, in this case, the sample distribution of the sample mean is exactly normal, with mean of x bar equal the true population mean, and sigma of x bar is called the standard error of the sample mean given by sigma model. Also, we mentioned that the standard error of the sample mean is always smaller than sigma. And also, as n increases, the standard error of x bar increases. So there is negative relationship between, or inverse relationship between the standard error of x bar and the sample size. That's when the population is normally distributed. So again, in this case, the new z-score is given by this equation. Here we replace sigma by sigma of x bar. So z-score is given by x bar minus the mean divided by sigma over root n. The second case, if the population is not normal, in this case we can apply the central limit theorem, and this theorem can be applied if the sample size is large enough. So if n is large, in this case we can say that the sampling distribution of the sample mean is approximately normally distributed as long as the sample size is large enough. And now, how large is large enough? We mentioned that for most distributions, n above 30 will give sampling distribution that is nearly symmetric or normal. But on the other hand, for fairly symmetrical distribution, n above 15 will usually give sampling distribution is almost normal. So we have three cases. One, for most distributions, we need large sample to be n above 30. For symmetric distributions, n above 15. But if the population is normally distributed, then regardless of the sample size, the sampling distribution of the sample mean is always normally distributed. So here it's nearly symmetric, almost symmetric, and the other one is always symmetric. So we have to distinguish between these three cases. And I think we gave one example. Now let's move to the another part. As we mentioned in the beginning of this class, data has two types mainly, quantitative and qualitative. Quantitative, for example, your score. Score is numerical values, 60, 65, and so on. In this case, we can talk about the sample mean. So first, for quantitative data, we talked about sample mean. This is number one. Number two, if we talk about qualitative data, in this case we talk about sample proportion. In this case, the question is, what's the sampling distribution of the sample proportion? So we are looking for the sampling distribution of the sample population having some characteristic. For example, let's buy denotes number of smokers among females. So let's use Y as number of smokers among all females. all females at iug. So here we are talking about my population is iug students, but here we'll focus on female students. And pi is number of smokers among all female students. Now sample proportion, so my characteristic here is smokers. Maybe your characteristic is person or students number proportion. I'm sorry, it's proportion of proportion, not number, proportion. The proportion of students have scores above 80. So pi proportion of students have scores above 80, and so on. So here, in this case, your characteristic is scores above 80, and so on. Sample proportion provides an estimate of pi, because generally speaking, pi is not given or is unknown. Similar as mu. Mu is the population mean, is always not known, and we are interested to estimate the population mean. In this case, the point estimate of pi is p. So p is the point estimate sample and proportion, which is the point estimate of pi. Now, for example, let's go back to the proportion of smokers among all female students at IUG. Let's assume that number of females at IUG, for example, is 1,000 students. And we took here around a sample of 1,000. We know that there are too many female students at IUG. Suppose we select a random sample of size 1,000. So that's the sample size. So here we selected a random sample of size 1,000 from the population of females. And suppose we found that number of smokers among these equal 100. So out of 1,000, 100 students are smoking. Now, what's the percentage of smokers in this case? 10%. So P equal this 100 divided by 1,000, so that's 10%, or 0.1. Let's assume that X denotes the number of items in the sample having the characteristic of interest. In this case, smokers. X number of smokers in your sample, so X equal 100. N is 1,000. So the proportion is always equals X divided by N. X number of items and the characteristic you have. N is the sample size, so B equal X over N. Sometimes might be X equal 0. So for example, suppose I select a random sample of size 1,000 and none of them is a smoker. So in this case, X equals 0. That means the percentage equals 0. So we can have 0% if X equals 0. Also in the upper limit, suppose here we are talking about students have scores above 80. And we select a random sample, and that sample has all of the students have scores above 80. So that means X equal 1,000. So percentage is 1. So 1,000 divided by 1,000. So the minimum value of B is 0. The maximum is 1. That means B ranges from 0 to 1. So it could be 0, it could be 1. But almost B is between 0 and 1. B is the proportion. So B is, in this case, is approximately distributed as normal distribution when N is large. But again, How large is large enough? We'll talk about later. So B is approximately normally distributed when n is large. Here we assume sampling distribution with replacement if the population is finite, and sampling without replacement from infinite population. Finite population means limited, has fixed size. Infinite population means unlimited. Because if we select a random sample without replacement from infinite population, for example, suppose n equal 10,000. In this case, each person has a chance of being selected 1 over 10,000. Let's assume that we select sampling without replacement. So in this case, if we select one with a proportion of 1 over 10,000, it means the second one has a chance of 1 divided by 9,999, and the difference between these two is very small. For this reason, we can select a random sample without replacement if the population size is large, because the probability to select an item from that population remains the same, or approximately the same, because 1 over 10,000 is roughly equal 1 over 9,999. Now, the two conditions we have to check in order to apply, or in order to say that B is approximately normally distributed, the two conditions are n times pi is at least 5, and we have n, pi is given. Also, n times 1 minus pi is at least 5. So there are two conditions should be satisfied in order to use the normal distribution. Again, the first one, n times pi is at least 5. n times 1 minus pi is also at least 5. If these two conditions are satisfied, then you can say that B, or the sample proportion, is approximately normally distributed. So that's the shape of the distribution, with mean of mu of B equal pi. So the mean of B equal pi, where sigma of B equals square root of pi times 1 minus pi divided by n. So that's the mean of B is always pi, and sigma of B equals square root of pi times 1 minus pi divided by n. Let's compare this result with the sampling distribution of the sample mean. If you remember, the mean of x bar was mu, and here the statistic is the sample mean, and the mean of x bar is mu. On the other hand, the mean of the statistic, my statistic, is the sample proportion is pi. So in the two cases, the mean equal the true value. I mean the true parameter. So in this case, the mean of x bar equal mu, and mu of b equal pi. On the other hand, the sigma of x bar was sigma over root n. It looks similar, so because this one is just sigma square over n. But here sigma square is pi times 1 minus pi. Now, so again, the sample distribution of B is roughly symmetric, or approximately normally distributed, if these two conditions are satisfied, and mu B equal pi and sigma B equal square root of pi times 1 minus pi over n. Now, this score, as we mentioned before, the standard equation is given by x minus the mean of x divided by sigma. Last time, we talked about sampling distribution of x bar. So your z-score equal x bar minus the mean of x bar divided by sigma of x bar. So that's x bar minus mu because the mean of x bar is the mean, divide by sigma of x bar, sigma over root n. Now let's compute z score for p. So z equal p minus the mean of p divided by sigma of p. So in this case, z equal the mean of b, which is pi, divided by pi, 1 minus pi divided by n. So in this case, the new formula for the z-score is given by pi minus 1. So this here is z-score, z equal pi minus p minus pi divided by root pi times 1 minus pi divided by small size n. Now let's do one example. The example says that if the true proportion of waters who support proposition A is 40%. So in this case, pi is 40%. The question is, what's the probability that a sample of size 200, so we select a random sample of 200, yields a sample proportion between 40% and 45%. So in this case, we are looking for the probability between 40 and 45%. Now, if the problem says the true proportion, it means pi. The true mean, it means also mu. So true, it means we are talking about the entire population. So true proportion, it means the population proportion. So the word true in the statistics, in this case, means population. So the population proportion equals 0.4. So pi is equal 0.4. Now, if pi equal 0.4 and the sample size is 200, what's the probability that this sample proportion lies between 40 and 45%? Now, in order to use this score, you have to check the two assumptions. But since n is large enough, n is 200, for sure the two conditions most of the time are satisfied. But you have to check in order to apply this score. Let's see first how can we check the two conditions. Now, n equal 200, pi is 40%, so n times pi is 80. 200 times 0.4 is 80%. So the first one is satisfied, the first condition. Can you figure out the value of n times 1 minus pi without calculation? Exactly, 200 minus 80. So this value is 200 minus 80. Or just 200 times 1 minus 0.4. 200 times 0.6 is 120. So if you just find the first one in times pi, the other one is n minus 80 will give the other condition. So now the two conditions are satisfied. Then we can use the z-score. I mean, we can say that the sample proportion is normally distributed with mean equal pi, always pi, and pi is given as 40%, and the sigma of p equals square root pi 1 minus pi divided by n. That's the square root of 0.4 times divide by 200. And that will give 0.03461. So the first step, we have to check the two conditions. Second step, compute the mean of B and sigma of B. Now, finally, find the z-score of your problem. Here he asks about what's the probability that B lies between 0.4 and 0.45%. So we have to find z-score for 0.4. So that's 0.4 minus, again, the mean of B, which is again 0.4. So this value divided by 0.0346. So again, B is 0.4. This is pi. And pi, in this case, is always 0.4. And this is your B. So 0.4 minus 0.4 divided by 0.0346. This one equals 0. The other z-score, for the other value, here 0.45. And this gives 1.44. After that, this problem is converted to standardized normal value. So we, instead of B, we have Z between 0 and 1. That's all for using chapter 7. Now, to complete your answer, you have to use chapter 6. Now, B is between 0 and 1.44. As we mentioned many times, the area here equals, the dashed area equals B of Z less than 1.44.
Minus 0.5.
Exactly minus 0.5, because the area to the left of 0 is 0.5. Now, by using the normal table, or standard normal table, P of Z is smaller than 1.44 is given by 9,251. Just check your table. Minus 0.5, so the final result is 0.4251. That means around 42%, 0.51, that the proportion lie between 40 and 45%. So that's how can we compute the probabilities underneath the normal curve if we are interested in the sample proportion.
Teacher, if some condition not happen.
Now, in case if one of these conditions is not satisfied, we cannot use this score unless we increase the sample size. So here, the two conditions should be satisfied. For example, suppose n equal 200, but this probability of pi is 1%. Suppose, again, n is 200 and pi is 1%. So this condition is not satisfied because n times pi is just 2. So you cannot use the z-score because it should be at least 5. So even if the sample size is large, maybe one of the conditions is not satisfied because you have a small true proportion. So if the true proportion is very, very small, in this case you have to increase your sample size. Make sense? Any question? Now I will discuss some practice problems for chapter 7. Let's do some practice problems for chapter 7. I will give some multiple choice problems first. Number 1. We have 4 choices. Parameters. Now, sampling distribution always describe the sampling distribution of a statistic or statistics. So, not parameters, we have to choose the statistics. So, sampling distributions describe distribution of always statistics. Next, the central limit theorem is important in statistics because we have 4 choices. Let's see why C is correct. Part A says for a large N, it says that the population is approximately normal. We cannot say the population is normal. The sampling distribution of a statistic is approximately normal. So for this reason, the part A is incorrect. For the other one, for any population, so regardless of the population, it says the sampling distribution of the sample mean is approximately normal regardless of the sample size. This is incorrect because it says for any population. So B is incorrect. But if it says for normal population, then we can say the sampling distribution of the sample mean is approximately normal regardless of the sample size. But it says for any, so that means incorrect. Now, part D, for example, for any size sample, it means regardless of the sample size. The theorem says the sampling distribution of the sample mean is approximately normal. That's incorrect. Part C, for large N, it says the sampling distribution of the sample mean is approximately normal, regardless of the shape of the distribution. That's true, because here we have large sample size. So regardless of the population, the shape of the population, we can say that the sampling distribution of the sample mean is approximately normally distributed. Number 3. Which of the following statements about the sampling distribution of the sample mean is incorrect? Here we are looking for the incorrect statement. Look at A. The sampling distribution of the sample mean is approximately normal whenever the sample size is sufficiently large. This is correct. B. The sampling distribution of the sample mean is generated by repeatedly taking samples of size n and computing the sample means. That's also correct. The mean of the sampling distribution of the sample mean is always equal to mu. That's correct, because we know that the mean of x bar is a mu. Now, the standard deviation of the sampling distribution of the sample mean is equal to sigma. And yes, exactly, the standard error, which is sigma of x bar, not sigma, equals sigma divided by root n. For this reason, this one is incorrect statement, because we have to divide this sigma by the square root of n. Number 4. Which of the following is true about the sampling distribution of the sample mean? Again, the mean of the sampling distribution is always mu. That's correct or statement. Now look at B. The standard deviation of the sampling distribution is always sigma.
No.
Incorrect, because sigma over root n. Part C. The shape of the sampling distribution is always approximately normal. If n is large, then we can say it's approximately normal. All of the above are true, is incorrect. So that's number 6. Look at number 10. Number 10. Telemarketer set the company's computerized dialing system to contact every 25th person listed in the local telephone directory. So the company select the person that in the 25th position. So the 25th person is being selected. The other one is the first item. The second item should be, in your case, 25th. So the fifth, so 1, 2, 3, 4. So number 25th, the first item. Maybe you have something more. Then the second item is number 50 and so on. What sampling method was used? A systematic sample because we choose the 50th person. Then the second one is the 50th and so on. So 25, 70, 50, 75 and so on. Number 11, which of the following methods will more likely be susceptible to ethical violation when used to form conclusions about the entire population? Now the correct answer is convenience sample. Because number one, convenience sample is used because it is easy, inexpensive, costly, and it's used, we select the sample if it is convenient to the researcher by himself. But maybe in this case we have biased collection. For this reason, this is incorrect sampling. Most of the time, we are going to avoid using this technique unless your sample is unbiased. Because if, for example, suppose I love tea of type A. And my sample, I select a sample of size 20. Since I love type A, I choose these 20 students or 20 persons that like tea of type A. That means your sample is convenient for you, but it's biased. Okay, so in this case, it's called convenience sample, so it will give incorrect results. So it's convenient sample. Let's do the other section, one of these problems, true or false. Let's do some of these. Now for true and false problem, try to avoid calculations as much as you can. Just solve the problem without any computations. Maybe simple calculations might be used, but don't use the exact calculations because the problem asks just true or false. So sometimes the problem makes sense, the answer is true, so just say true without doing the complete calculations because you will waste time, because as you know we have exam of just 60 minutes. And for true and false, I expect your answer to be within, for example, 15 seconds. Or just read the problem, then figure your answer. So in this case, sometimes you don't need to do the exact calculations. But for the free response problems, you have to do the calculations. But here, just think about it a little bit, and within a few seconds, you can figure out if it is true or false. Now, let's think about number one. Now, each of these problems, I will ask all of you to figure out the answer, and I will give bonus 1 point for each one. Forget about the answer, is it true? I need explanation. Why is it true? Now let's see. The amount of time it takes to complete an examination has skewed left distribution with a mean of 65 minutes and standard deviation of 8 minutes. If 64 students were randomly sampled, so we select a random sample of 64. Now we ask about the probability that the sample mean of the sampled students exceeds 71 minutes is approximately 0. Probability that the sample mean of the 64 students score above 71, this probability is approximately 0. So the problem says the amount of time it takes to complete the final examination is not normal, it's left skewed to the left. Here we select a random sample of 64 students. That gives sample mean of 65, and we have standard deviation of 8. Now, the population by itself is not normal, and the population has mean of 65, as we mentioned, and standard deviation of 8. Now we select a random sample of 64, it's large sample size. What's the probability there? The sample mean exceeds 71. It says the answer is approximately 0. Think about it. Why the answer is true in this case?
Might be because 71 is more than the sample size.
So the first guessing here is just 71 is above 65. Yes.
We can apply the CLT theorem because L is above 30, so we can consider that this distribution is normal. So we transform from X bar to standardized and do other calculations.
That's correct, but to do the problem, the complete answer, yes, you have to convert to the score because n is large. Then you can figure out the answer. So she said that. But I'm looking for something different. First, convert to z over root n, sigma is 8, divided by a square root of 64, which is also 8. So this is z greater than 1. I'm sorry, 6 divided by 1 is 6.
Now z greater than 6, if you go back to the normal table, now the table we have give the area to the right, to the left. So this one is 1 minus
z less than 6. 1 minus. For 6, we have 0.9999. So the answer is approximately 0. So it makes sense, it's 0. This is the complete answer. It takes time, because you have to convert to this score, do some calculations, then use the normal table, the standard normal table. I mentioned before, try to avoid this kind of calculations. Now, how can we figure out? Now, since the problem says skew to the left and n is large, we can assume that x bar is approximately normal. So don't worry about the shape of the distribution because we select a random size of size 64. So we can apply the central limit theorem. Any idea? Again, this way is true to do the complete calculations, but again you have to avoid using this. I will give you a hint. Now, 71, what's the difference between the true mean and the sample is 6. So, okay, so that's sigma of x bar is 8 divided by square root of 64 is 1. Again, continuous, just 1.
sigma equal
Why? The difference between 71 and 656 is 6, and 6 is 6 times the standard error of the sample mean. And we know that if you remember this rule, 65, 68, 95, 99, we don't use Chebyshev in this case because the distribution is roughly normal. We know this rule, the empirical rule. We said that 68% of the observations lie within one standard deviation of the mean. 95% two standard deviation and so on. Now, if you go back, now let's say mu minus 3 sigma and mu plus 3 sigma. But here we are talking about x bar. So the mean of x bar, sigma of x bar. So empirical rule says that this area between mu minus 3 sigma of x bar is around 99.7. Let's compute the lower bound. Mu is 65. 3 times sigma of x bar is 1. So that's 62. The maximum here equal mu again 65 and plus 3 times 1, 60. So now 99.7% of the sample means lie between 62 and 68. Now what's left? 0.3% for both sides. So that's 0.15 to the right and the same to the left. Now we are looking for x bar exceeds 71. 68 this point, 71 should be to the right. Now what's the probability to the right of 71? It's almost 0. Because since we are saying that most of the data lies within 3 standard deviations of the mean, now here the difference between this point 71 and 65 is 6. And the sigma of x bar is 1, so it means the difference between mu and x bar is around 6 times sigma of x bar. So you are sure that 99.7% of the data lies between 62 and 68, and just 0.3% of the area left to the other side, 2 sides, split in half. So we have 0.15 to the right and the other to the left. But again, we are looking for x bar exceeds 71, so we have to go further to the right side, so the area becomes very small. This method is faster. If you figure out this one, we can apply the empirical rule. Let's do similar questions. Look at the other one. Number 5. Number 5. Gasoline purchased per car at large surface station has population mean of 15. So the mean is 15. and a population standard deviation of 4. Sigma is 4. It is assumed that the amount of gasoline purchased per car is symmetric. There is approximately 68.16% a chance that a random sample of 16 cars, so n equals 16 cars, will have sample mean between 14 and 16. So it says that between 14 and 16, the answer is 68.14%. So again, we have a population, and this population is symmetric, with mean of 15, sigma of 4. We select a random sample of 16. The problem says that the probability of X bar between 14 and 16 equals 68%. And the answer is true. Apply. How can we apply or use the empirical rule in this case?
Mu minus 3 standard deviation, plus 3 standard deviation.
Mu minus 3 standard deviation. It says 68. 1. So it's mu minus 1 standard deviation, 1 sigma of X bar. And let's look at 1 plus sigma of X bar. Mu is 15. Now sigma of X bar. Sigma of X bar is also 1 because 4 divided by square root of 16 is 1. So 1 times 1, 14. On the other hand, 15 plus 1 times 1, 16. The problem says 68.4%, the answer is correct. Because we know that 68% of the data will fall within 1 standard deviation around the mean. So I think it's very quickly to get your answer rather than using the exact calculations, because for the exact one you have to do 14 minus the mean, divide by sigma, z, then 16 minus the mean, divide by 1. Then use the normal theta to use the empirical rule in this case. So if we select a sample of size 16, the probability that X bar lies between 14 and 16 is around 60%.
Look at number 6. Again, we assume we have the same information for the mean. Mu is 15. The same standard deviation is 4. But here, a random sample of 64 cars selected. So instead of select 16 cars, we select a random sample of size 64. Now it says there is approximately 95.44% chance that the sample mean will be between 14 and 16. So again, this probability between 14 and 16 is also
Mu minus 2
equals 9.44. Let's see if this is correct or not. Since it mentioned that 95%, so it means that we are talking about 2 standard deviations. So let's just compute mu minus
2 standard deviation
and plus 2 sigma of X. So the mean is 15. And minus plus 2 times again 1. 1 is not 1 because sigma of X bar was 1 because n was 16. Now my new sigma equal 1/2 because sigma over root n. Now sigma again the same value 4 divided by 64 over 8, so that's 1/2.
So this one should be 2 times 1/2. So that will give 15 minus 1, 14. 15 plus 1 is 16. The probability between 14 and 16, I mean X bar lies between 14 and 16 equals 95%. And we just changed some information a little bit, but the answer was the probability between X bar, the probability that X bar lies between 14 and 16 is around 68%. Now what's the difference between number 5 and 6? Okay, n is large. As n increases,
Standard deviation decrease.
standard deviation decreases. If you look here, sigma if X bar was 1, then my new sigma of X bar is 1/2. As we mentioned before, as n increases, sigma of X bar decreases. In this case, we have large probability. So if we increase the sample size, then the probability that X bar is between 14 and 16 will increase. So this proportion is increased around 30 or around 27%, because you just increase the sample size from 16 all the way up to 64. So since, as we know, as the sample size increases, sigma of X bar decreases, so we are more sure that X bar lies between 14 and 16. The previous one, the chance that, or the probability that X bar lies between 14 and 16 is around 2/3, around 68%. But here, for the same kind of probability, it's equal around 95%, because you increase the sample size. Any question? Let's do one more. Suppose mu equals 50. Mu equals 50. Sigma square, it means the variance is 100. So sigma, don't forget to take the square root of sigma square in order to find sigma. In a sample of 100, 95% of all possible sample means will fall between X bar between 48 and 51.9. This equals around 95%. Now without calculations, since it says the problem is normally distributed or n is large, in this case n is large enough to apply the central limit theorem, then we can use the empirical rule. It says 95%, so 2 standard deviation of the mean. So mu minus plus 2 sigma of X bar. Now mu is 50 minus plus 2 sigma of X bar. Yes, I have to compute sigma of X bar first. So sigma divided by is 1. So simple calculation, just sigma over root n is 1. So minus 1. 50 minus 2 is 48. 50 plus 2 is 52. So it's between 48 and 52. And this probability is 95%. So it's true. Now which is faster? To use this method, which is maybe less than 1 minute you can figure out the answer, or use the complete calculations. In this case you have to find z-score for the first one, z for the other one, then use the normal table, and that will take at least 5 minutes. So to use the empirical rule, most of the time gives shorter time. Any question? Let's do one more.
one more. Number 10. The amount of bleach a machine pours into bottles has a mean of 36. So the mean is 36. Sigma is 15 ounces. Suppose we take a random sample of size 36 bottles filled by this machine. The sampling distribution of the sample mean has standard error of, so standard error means sigma of x bar is 150. Again, it says the sampling distribution of the sample mean has a standard error of 0.15. I mean sigma of x bar is 0.15. It's false because sigma of x bar equals sigma over root n. So 0.15 divided by 6. So it's incorrect. That's false. False because this value is just the standard deviation. But he asked about the sampling distribution of the sample mean has standard error. And standard error means the standard deviation of the sample mean. So we have to divide sigma by square root of n. Next, 11. The mean of the sampling distribution of a sample proportion is the population proportion pi. That's true. Because if the two conditions we mentioned before are satisfied, then the mean of p is pi. So that's correct. 12, the last one. The standard error of the sampling distribution of p times 1 minus p divided by n, where p is the sample proportion, it's false because sigma of b square root of pi 1 minus pi divided by n. So this statement is false. طبعا. Let's look at number 13, the last one, number 13. A sample of size 25. So we took a random sample of 25. So n is 25. It provides a sample variance of 400. The standard error, he asked about the standard error, sigma of x bar, in this case equal to 4, is best described as the estimate of the standard deviation of means calculated from sample size 25. He asked about sigma of x bar. We know that sigma of x bar equals sigma over root n, but sigma is not given. S is a square. S is a 20. But what's sigma? Because sigma of x bar, sigma over root n. Sigma is not given. But as we know before, since n is large enough, so if n is large, in this case, if n is large, we can replace sigma by s, and this is just s over root n. So if n is large enough, n is more than 15, so we can use, or we can apply the central limit theorem. So we can replace sigma by s. So s equal 20 divided by 5 is 4. So the standard error equal 4 in this case. So if s square is given instead of sigma square, we can replace sigma by s if n is large enough. So in this case, we replace sigma by s. So sigma of x bar equal s over root n. That will give 4. S is the sample variance. Sigma is population s squared.
is sample variance. Sigma squared is the population variance.
We know that. S square is the sample variance, where sigma square is the population variance. And population in this case is not given. So we replace the population variance by sample variance. If the population is normal or n is large. Because if n is large enough, we can apply the central limit theorem. And if you go back to the formula for S, if you remember, we divide by n minus 1. And for sigma, we divide by capital. So if n is large enough,
No difference.
then there is small difference between sample variance and population.
Okay.
Okay. Any questions? Any question? If it is above 15, it's okay. 15 or 30, it depends on the population you have. But here, if you divide by 24 or 25, the difference is small. I mean, if you divide this one by 24 or by 25, the difference between S and sigma is small, so we can replace sigma by S if sigma is unknown. Questions?